let's start with differential calculus, because there's really two sides to calculus. The first one being differential calculus, and that asks, well, what is happening with change? How is something changing? Now with the line, the answer is very easy. So for a line, the answer is it's the slope. But what if I don't have a line? What if I have some other strange curve? Maybe I have a curve doing this. And I say, okay, how is it changing? And the answer is, it depends. On some points we can see it's going up. Some points we can see it's going down. So there's not one consistent change. But now we can change the question and say, okay, well, maybe it's not always the same, but how is it changing here? At that point right there. Well, what we can do is we can pull out our magnifying glass and zoom in. And if we zoom in, we see that it gets a little bit less wiggly. Say, okay, well that's good, but it's not very flat. Well, pull out your microscope. All right, so we pull out our microscope. We keep zooming in. And now, when we zoom in, it's becoming a little bit more flat. Say, okay, can we do better? Yeah, we'll go over into one of these science buildings, the ones that have money. And we'll say, pull out our scanning electron microscope. So we're really zooming in very close. And when we zoom in very, very close, what do we see? Well, we see something that is basically, for all intents and purposes, flat. So as we zoom in, our wiggly curve nearby, in the small, looks more and more flat. Now, this looks like a line. And that line has a particular name. It's called the tangent line. So when we talk about tangent lines, the reason that tangent lines are important is that's really the behavior that's happening locally. And now that we can approximate things by lines, we say, okay, now I can answer things about how change is happening. I can find the slope of that tangent line. Life is good. I know how to describe behavior. So that's differential calculus. Integral calculus asks a different question. The goal in integral calculus is to say, what's the total? Now, we'll be careful here. A lot of people think integral calculus is saying, how much area is there? But integral calculus is so much more. It's saying, how much of something is there? Now, the something varies based on context. Now, in things like calculus 2, you'll see there's things like volume, length, surface area. Depending upon the problem, you can actually say, what's the total? You could say total mileage. Suppose you know how fast your car is going. How far did the car travel? So there's all sorts of things. So suppose, we'll start with the area. It's a very basic idea. I have this x. I have f of x. And I want to say, well, how much did it change? I didn't make f of x very wiggly here. I should have, but all right. Well, if I want to find the change, or rather, excuse me, I want to find the total, I can think of it in terms of area. I say, well, the thing I know how to find area for is rectangles, because it's a flat thing. So what's the idea? Well, the idea is let's make this into a bunch of skinny strips. So we chop it up into little tiny pieces, and for each piece we say, look, I can approximate this part by a rectangle. And now I can get a good approximation for the total underneath by looking at these rectangles. Of course, it's an approximation. How do you get better? Okay, someone said limits. All right, that's correct. But here, what do limits mean? So limits are whenever you hear something like closer and closer or smaller and smaller. So the idea of limits, it's sort of a process of getting more and more refined, more and more precise. So yeah, we can chop it up into smaller pieces. And when you break up into smaller pieces, your errors get smaller, which means your approximation gets better. And of course, you could say, look, I can keep going, and that's the idea of limits. Keep the process getting better and better. Keep refining the process. So that's integral calculus. Now, which one of these two are we going to focus on this semester? The answer is both. we're going to do both differential calculus and integral calculus. Ah, good times. Good times. All right. So there's our review of calculus. Now, today, we're going to start off pretty simple and just remind ourselves a little bit about geometry. Now, calculus is motivated by geometry. And if you look at the word geometry, it's actually a very interesting meaning here. Geo is earth, like if you've had geography. That's about earth. So earth, metry is measure, measuring the earth. So math came out of very practical applications. They want to know things. How far away is that? How tall is that? How much is there? Now, the Greeks started with geometry. They did geometry a little bit differently. They just said, okay, there's this space here, and I can talk about things like points, and I can talk about things like lines. Now, when we think about geometry, we think about coordinate systems, which is a little bit more modern. The Greeks didn't have coordinate systems. So for us, we think of what are called the Cartesian coordinates. And so this comes from a mathematician, philosopher named Descartes. And legend goes, one day he was sick, laying in bed. This was before they had Xbox, didn't have a lot of entertainment. So he's just staring at the ceiling. There was a fly up at the ceiling. And he thought to himself, I can describe where that fly is at any time if I can say how far away it is from this wall, how far away it is from this other wall. So in other words, by a pair of distances, it could describe the location. And that's what happens in 2 dimensions. So here we have axes. So we set our axes in space. There's the origin is called 0, 0. There's one direction. We tend to call it the x-axis. Another we call the y-axis. So the x-axis are points of the form x, 0. Y-axis is points of the form 0, y. And then every point can be described as a pair, x, y. All right, so that's the coordinate system. Now for distance, because we want to measure things, that comes down to the Pythagorean theorem, which is a really beautiful theorem. Now, Pythagorean theorem says, suppose you have a triangle, but not just any kind of triangle, a right kind of triangle. So you have a right triangle, and you know the lengths of 3 sides. Then if you take the length of one of the sides squared, add the length of the other side squared, that's the length of the hypotenuse squared. A squared plus b squared equals c squared is how it's often remembered. So if we apply that for our pair of points, x1, y1, x2, y2, the length in the x direction, that's the size of x2 minus x1. When I say the size of absolute value, it's the magnitude of that. On the other direction, it's y2 minus y1. And therefore, Pythagorean theorem says the distance between the 2 points squared is x2 minus x1 squared plus y2 minus y1 squared. Now you take the square root, and there we get our distance. And now the introduction of one of our largest nemesis in calculus, the square root. It is a nightmare to deal with. And the good news is that there are ways to deal with square roots. It's not always possible, but there are many cases where it is. And the very thing which causes the square roots is what allows us to solve it. But that's a good Calc 2 story. So you've already heard that one. All right. Well, let's go up to 3 dimensions. So now in 3 dimensions, we're going to have 3 different values, x, y, and z. These are all measuring distances of amount traveled. So I have 3 different directions. So the nice thing about the 3-dimensional coordinate system is it's a coordinate system we're very comfortable with because we live in 3D. So we can get behind that. So we live in 3D. So oftentimes, if you imagine you're in a room, you can go stand in the corner. And what happens is that the vertical part, up and down, we can think of here, that's the z direction. If you're standing against the wall, what's on your right-hand side would be the x direction, and what's on your left-hand side would be the y direction. There is actually a choice that was made here. about whether you should have x going this way and y going this way or vice versa. So there is a choice. And so this is sometimes called the right-handed coordinate system. You can have left-handed coordinate systems, but universally this is the one that we'll go with. All right. Well, what do we need to know? Now, in 2 dimensions, we talked about the axes. In 3 dimensions, we still have axes. So I can go in the x-axis, that points to the form x, 0, 0. Or I can go the y-axis, 0, y, 0. Or I can go the z-axis, 0, 0, z. So the axes are when we only are perturbing one variable. So the rest are zeros. But I can perturb 2 out of the 3 variables. So for instance, if I look down here, I see x, y, 0. Anytime when I can vary x and y, but I keep z 0, for example, I have this floor here, that's called the xy plane. And the idea of the xy plane is x and y are what's varying. But of course, there's more than just the xy plane. I can vary x and z. So that would be the xz plane. And probably not too surprising here, there's one more, and that's called the yz plane. So you'll hear us refer to these planes from time to time. So whenever you see a plane name, it helps you identify what it is. If you hear the term xy plane, that's everything in the form xy 0, and so forth and so on. Now, what do? Well, every point is described by an x, a y, and a z. Now, what if I want to know, if I'm on the xyz point, and I want to know the distance down to the xz plane, or how far am I? The answer is I just go straight down and I look at xy 0. So essentially you can say z is how far away you are from the xy plane. But I could ask a different kind of a question, not how far am I from a plane, how far am I from an axis? So if I'm at xyz, if I want to get to an axis, I'd go across the top of this box, and I'd shoot over to 0, 0, z. So this distance here would be the distance to the z-axis, which you can find by the use of the Pythagorean theorem. Well, let's just do distance very quickly. So how do you do distance in 3D? The answer is, it's the Pythagorean theorem again. But the Pythagorean theorem plus plus, because you get to use it more than once. So if I'm thinking about the distance, I can think about it as going from the corners of a box. So I have a point x1, y1, z1. I want to get to x2, y2, z2. They're opposite corners in the box. And the length of the sides of the box are the difference in the coordinates. So there's a difference in the y's, there's a difference in the x's, and there's a difference in the z's. Now, what we want to do is we want to not have to recreate new tools, but we want to use existing tools. So one of the things we can do to get started is to say, hey, let's just cover up the top. And suppose I wanted to get from this corner to that corner, not of a 3-dimensional box, but of a 2-dimensional rectangle. Because we've done that before. All right, well, if we look, what we see here is we see that there's a little right triangle sitting there. So I can say that this distance here, c, well, that's c squared. That would be this length squared plus that length squared. So I can find c by the Pythagorean theorem. Now, how do we find the total distance? Well, once we know c, we also say I know that length and I know this length. And again, there's another right triangle sitting there. And now I can say, well, the distance squared that I want is this length c squared plus z2 minus z1 squared. And I replace c squared by what I know what it is. And now I have what I want. I have my distance formula. Of course, the same sort of process works in any dimension that you want. All right. Well, last thing for today. Spheres. A sphere is a set of all points which are distance r from a center point. So spheres they're like the candy coating shell on an M&M. When I talk about a sphere, I'm not talking about a solid sphere. I'm talking about the sphere as just what's exactly distance r away from the center. It's a distance type relationship, so we can use a distance formula. So if I want to use a distance formula, I say, okay, I have a center HKL. That would become the x1, y1, z1, HKL. Then my points are x, y, z. And then the distance is the radius. So it becomes x minus h squared plus y minus k squared plus z minus l squared equals r squared. So the formula for a sphere pops out immediately from the formula for distance. Now, I talked about that can decoding. Well, what if you want to be in the inside of that sphere? Well, that says I need to be closer than the outside. So now you change your equality to an inequality. So if I want to be in the inside, I just want to make sure my distance is smaller than r. So it becomes less than. If I want to be on the outside, it needs to be more than r, and so it becomes greater than. All right, maybe a few more examples. Examples are always good. Test our understanding. Find the center and radius of the following sphere. Well, there's nothing written down here, so we're going to have to come up with something. All right, so here we go. Well, we're going to have x squared plus y squared plus z squared equals something. We'll make some stuff up here. So let's say 6x plus 10y minus 12z plus 11. Okay, just some numbers. Just some numbers. Now, the first thing you might say is this a sphere? I mean, I say it's a sphere. The problem says it's a sphere. But how do we know? Now, here's the general rule of thumb. When you see something with the x squared and y squared and z squared, that's a pretty good sign you're probably dealing with a sphere. Now, you might say, well, what about these other terms here? Because certainly, if we covered that up, then that would be a sphere centered at the origin, and then that plus 11 gives you a radius of roughly square root of 11. But these things change. The question is, what are they changing? So to understand that, we sort of say, okay, well, what's the right form for a sphere? Let's make some notes. So recall, it's x minus h squared plus y minus k squared plus z minus l squared equals r squared. So we really want to have just a single x and a single y and a single z. And right now we don't have that. See, we got the x on one side, but it's also on the other side. Similarly with the y, similarly with the z. So what we want to do is we want to put all the x's together. So I'm going to move stuff around. So when we move stuff around, we've got to be careful. So we've got x squared minus 6x plus y squared minus 10y and plus z squared plus 12z, and that's all going to equal 11. All right. I don't think I left myself enough space in some of these places, but that's okay. What's the moral? Well, the moral is this part here should be inside of that x minus h quantity squared. So how do we get there? Well, remember, it's a square. So x squared minus 2hx plus h squared. So we've got the x squared part. So that tells us that this minus 6x, that's that, like that minus 2hx. So what we need is we have that one more piece here that needs to correspond to h squared. And it's actually pretty easy to figure it out. This is called completing the square. Take this middle term and divide it by 2. The reason is that's minus 2h, right? So we want to divide it by 2. If we do that, we'll get negative 3. That's what h is. We square that and we add. So I put plus 9, and then I'm like, wow, woohoo, that's a perfect square. That's x minus 3 squared. Now there's a problem though. If I add 9 here, I've changed stuff. So I have to balance it out. Now there's a couple ways. I could immediately subtract 9, or alternatively I can add 9 to the other side. And that's the one I'm going to opt for. And we're going to go through and do this for each one. So we did it for the x. For the y squared, well, I didn't leave myself enough room. But again, the process, divide by 2 would be negative 5. Then I want to add 25. So there's a plus 25 that goes there. And if we have that, that's y minus 5 squared. okay, plus 25. Now z squared plus 12z, okay, divide by 2 square plus 36, okay, plus 36. Now that becomes z plus 6 squared equals, well, 20 plus another 25 makes 45, then plus another 36, and oh wow, that's actually a nice number. It's 81. Cool. All right. Didn't expect it to be so nice. Well, sometimes you make a mistake and things work out nicely. All right. So what's the answer? Well, we need the center and the radius. And now that we have it in this kind of format, we can read it off. So for the center, we get 3, and then 5, and now be careful here. See that plus? Because it really should be a minus. So think of it as minus minus. So the center is going to be 3, 5, negative 6. How about the radius? Well, the radius, r squared, 81. Well, square root of 81 turns out to be nice, 9. And there you go. So it turns out that what's happening is that these pieces are kind of doing two things. One, they're shifting the center at, because like I said, if we'd ignored them, we'd be at the origin. But we're also sort of changing what the radius is. And you got to be careful. Got to take everything into account. All right, so moral, okay, if you have x squared plus y squared plus z squared, and they're all being added, well, we can manipulate, complete the square, move stuff around. It's a sphere. And we can figure out what sphere it is, where the center is. Life is good. Life is good. Now let's do another problem. Very different flavor. Find the values for A so that the two surfaces, x squared plus y squared plus z squared plus 1 is equal to a squared plus 2z, and x squared plus 4a squared plus y squared plus z squared equals 4ax plus 2z intersect in one point, one single point. Okay, well, now they use the word two surfaces, but we know what the surfaces are because we see x squared plus y squared plus z squared and x squared plus y squared plus z squared. So these are spheres. All right. All right, so we know they're spheres. Well, we do the same thing we just did. So for the first one, what can we do? Well, we'll take the 2z and move it over. And what do we get? We get x squared plus y squared plus z squared minus 2z plus 1 equals a squared. Well, that's x squared plus y squared plus z minus 1 squared. I don't know why I put a parenthesis there. Okay, we'll put another parenthesis, doesn't matter. Equals a squared. All right, so good, good. Now, what's the other one? Well, here we're going to move the 4ax and we're going to move the 2z. So we'd have x squared minus 4ax. Now, what do we need to add? Divide by 2. That'd be 2a squared. So plus 4a squared. Good. Well, good news. We already had that. Oh, all right, good. So this is perfectly set up. It's almost like they wanted us to solve it. Y squared plus z squared minus 2z. Well, again, what do we need to do? Well, in fact, we can see it. We need to have z squared minus 2z plus 1. So it worked once, it's got to work again. And if we added 1, we have to add 1 over here as well. So this becomes, well, x minus quantity 2a squared plus y squared plus z minus 1 squared equals 1. So what do we have? Well, we know the centers. The centers are at 0, 0, 1, and radius here, just be careful, you want to say A, and you're probably thinking, it's A, right? Well, it's the square root of A squared. A, we don't know whether it's positive or negative. So the radius is actually absolute value of A. Now that's one. The other one, the center is at 2a, 0, 1. What's the radius? Well, the radius is 1. Now, how can we have things intersect in a single point? Now, one of the things is we should build up our intuition. If we're having a hard time in 3 dimensions, we can build up our intuition by saying, well, what's the equivalent thing in 2 dimensions? So, for instance, instead of saying, well, I have a sphere, and there's another sphere that's touching it at a single point, well, the intuition is, look at the picture, simpler, circle and circle. Now, what we're trying to do is build up the analogy. How do we understand this? How does it work? So, in our case here, we could say, well, look, suppose that this is the configuration. Well, what needs to be true? Well, if they touch at a single point, what has to be true is that the distance between the 2 centers has to be equal to the sum of the radiuses. So, what's the distance between the 2 centers? Well, we have the distance formula. So the distance formula would, you say you take the difference in x squared, the difference in y squared, the difference in z squared, but notice that the y and z are the same, so the distance between the centers is going to be a very simple formula. It's going to be the following. Whoops, takes a second to write down the distance between centers. Is going to be 2 absolute value of a. Now, we need to have it be the case that in order for them to touch, it has to have that this length and that length. In other words, the 2 radiuses added together have to get the right value. So size of a plus 1. Okay, so that's what has to be true. The distance between the centers is the sum of the radii. In other words, the 2 pieces added up. Well, all right, rearrange. You can subtract absolute value of a, and we can conclude that this says, hey, absolute value of a has to be 1. Well, that says really a is really plus or minus 1. All right, so there's one possibility. Now, you might think, well, wait a second, that's all possibilities. But let's think about it. Is there another way for 2 circles to touch at a single point? And just the generic picture. The answer, as it turns out, yes, there is one other way for 2 circles to touch at a single point. And that is to have the following. To have one circle inside of another circle. Now, so if that's the case, if I have one circle that's inside of the other circle, then they can touch at a single point. See, it's a slightly different configuration. All right, so what needs to be true in that case? Well, in that case, what has to be true is if I look at the distance here between the 2 centers, that's the same as the difference by taking the large distance, subtract the small distance, of course. You know, what does that mean? You know, you look at the absolute value of the differences of the lengths. So what's the distance between the 2 centers? Well, it's still 2 absolute value of a. So this has to equal absolute value of a minus 1. In other words, this is the difference in magnitude of the size of the centers. Well, this leads to 2 possibilities. So one possibility, we could say, well, what happens, say, if absolute value of a is fairly large? It's bigger than 1. So if that were the case, 2 absolute value of a would have to equal absolute value of a minus 1, if it were large. But that would say what? Well, that would say, subtract absolute value of a, absolute value of a is negative 1. No, that can't be. Wah, wah. Okay, so that can't possibly be the case. So it must be the case that, in fact, the absolute value of a has to be fairly small compared to 1. So, in fact, what we have to have is that 2 absolute value of a has to equal the negation of this, which means we flip the sign. So it becomes 1 minus absolute value of a. Move the absolute value of a across. 3 absolute value of a equals 1. Well, that really says the absolute value of a had better be equal to 1/3, or a is plus or minus 1/3. Therefore, there is a grand total of 4 possible values for A. Positive 1, negative 1, positive 1/3, negative 1/3. All right, good. Now this is a little bit more challenging, but really it comes down to understanding how can I think about these things in relationship to one another. And once we understand, like, look, don't focus on the 3-dimensional thing if it's throwing you off. What's the 2-dimensional? The 2-dimensional can help you build intuition. And once you start building intuition, you build understanding. And we want to understand things. That's our goal. We want to understand all the things. All right, good. That's it. Done.